you for interaction. Thank you for coming as well, especially after yesterday events. Uh, I hope I will not bother you much because today I will present you some uh, projects that we are focusing on at Brno University of Technology. Especially, I will talk about the Network Traffic Encryptor, and we can start right away. First, let's introduce ourselves. I am from Brno University of Technology. We have several research and development processes that are running right now. Our main focus is, however, on post-quantum cryptography, some industrial networks, privacy enhancing technologies, and some projects for the state, especially for the Ministry of Interior. Also, for companies and individuals, we offer some services in ICT security, namely stress testing, DDoS testing, and also some servers that can secure your infrastructure from the DDoS attacks. Let's get to it. So, Network Traffic Encryptor, what it is, why do we bother with it? It's a project in which we were tasked with creating a post-quantum secure network traffic encryptor, both hardware-based and software-based, that can be used in factories or for personal use or for commercial use, small and big businesses, and this is the result. The hardware network traffic encryptor. It's based on the FPGA cards, so it's offering high speed, high capacity, high throughput, also very customizable. The only downside to it is the cost, which is slightly higher just because it's a very custom hardware. The architecture of the encryptor is very simple, I guess. We implemented our own key creating mechanism, which generates a key from 3 separate keys. The first key that is going into the combiner is the ECDH key. We use ECDH 512 curve for the key establishing. The next one is the PQC, in which we use the Kyber 768 algorithm. And last is quantum QKD, just another any QKD server you can think of. We were testing it with the ID Quantic infrastructure. After the keys, these 3 keys are then combined in the key combiner and fetched to the AES 256 cipher, which is then securing the connection as a whole. With this particular encryptor, we have reached speeds up to 100 gigabytes per second. With the software encryptor, we will get to it later. There is not such speed, but it offers another pros. Here are some test results from the hardware testing. It was all tested in the lab environment. In the first table, we can see the throughput that is based on the packet size. From some 512 bytes of packet size, we can see that the throughput is stable at 100 gigabytes per second. Then there are some figures on the delay, which was a big problem that we were interested in solving. The initial delay, which represents the delay between the idle to fully active regime, it's based on clock cycles, and we can see that from a certain amount of data size, the initial delay is quite stable. as well as the delay between changing the data. Now, some few slides about the software network traffic encryptor. This is based on the OpenSSL library, as well as some open quantum safe provider functions, and the Crypto++ library as well, because it's implemented in C++. It's totally open source. You can view it or download it, test it on my GitHub if you want. The functionality regarding the key creation and encryption as a whole is the same, mostly. Here you can see the architecture. Basically, side A and side B are considered trust zones. The individual keys are established via their respective connections, and then the secure connection, the post-quantum secure connection, is established at the end with the AES256 key. I don't want to forget to mention that I said you have three keys from which you derive the symmetric key, but it do not have to be like that, because both on the hardware and on the software, if you just happen to not have a QKD server in your basement, it's not a problem, because you don't actually need it. Both the encryptors can run without it, and it's not jeopardizing any security or anything like that. Also, of course, we are using the AES, so we need to think about the periodical key exchange, mainly on the hardware encryptor, and that's because of its high throughput. If we have average throughput about 100 gigabytes per second, then the key would be vulnerable after only 8 minutes. So we have established that the annual key rate change will be every minute. Here the speed is not so high, so here the key is exchanged every 1 hour. The testing with the software network traffic encryptor was, at least for me, more interesting because we tested with in 3 different scenarios. One was basically just on virtual machines, in which we just tested the functionality. Then we were very interested in testing it on some low-end computers. So we tested it on Raspberry Pi 4s. You will see the results of this test on the next slide. And lastly, we have cooperated with our partners in Estonia, namely with Cybernetica, to create a pilot connection between the Czechia and Estonia using this encryptor. With the software encryptor, we mainly focus on throughput, delay, and influence of rekeying on continuity of communication. The third one was kind of tough, but I think we have managed to resolve it. Here you can see the test results. The first figure shows the test results from the virtual environment. Basically, we can see that encryptor works better than the OpenVPN, but the results are worse than for WireGuard. That's mainly because WireGuard is very benefiting very much from the kernel implementation, which we do not have it. In the next figure, we can see the impact of rekeying, as I was saying. This was a huge problem to solve. You can see here on the timeline, every 1 minute is a new rekey, and you can see that dips at the rekeying. This whole project was a part of the NESPOC project, which was funded by the Ministry of Interior of the Czech Republic. The planned results were the hardware encryptor. Mainly, the software encryptor was just some like student project that we have created, like a twin for that, I would say. And we have a continuing project that will, I hope, follow up with this, and where we can more develop the hardware encryptor, polish some bugs that we encounter along the way, and hopefully create some useful encryptor for everyone to use. So that is all from me. I thank you very much for your attendance, and I'm open to questions.
Thank you. Awesome project. Could you elaborate a little on how you derive the AES keys from the 3 key exchange keys?
Is the question how we derive the AES key?
Yes.
Yeah. Basically, it's a combination of HMAC and SHA functions. It's like I don't have a picture of there, but it's look like a small tree, and basically you are just storing with the particular keys with the using the HMAC functions together until you are left with only one key for AES.
Thank you.
Great. Any other question? I think it was great enough, you know. So big applause for Jan Havlin. Thank you so much.